Okay, if we can do this with 3 input variables, can we do it with 4? Now, with 4 input variables, we've got a total of 16 minterms that we've got to keep track of. Now, the nice thing about 16 is we can put it in a 4x4 grid. So let's see if this is going to work. I'm not going to write the whole truth table. Just remember, if we're talking about W, X, Y, Z, then it's looking like 0, 0, 0, 1, 0, 0, 1, 0. I guess I should start with 0, right? 0, 0, 1, 1, and so on. We get to 0, 1, 1, 1, and then 1, 0, 0, 0. And all the way down. We've got 16 different minterms, but we're still tracking. So this is W, X complement, Y complement, Z complement. We're still using the placement of the uncomplemented literals to represent the ones in the number that is the term. So this is 1, 0, 0, 0. So it's minterm 8, just because 2 to the 3 is 8. Just reminding you how minterms work of 4 variables. Okay, so we've got 4 variables to worry about, and we've got to put them in a grid. So we have to put them in the grid so that each square, each cell, has a minterm adjacent to it that differs by only 1 literal. I don't see any reason not to keep what we had for the 3 variable case. 0, 1, 2, 3, 4, 5, 7, 6. We might be tempted to then write 8, 9, 11, 10. But minterm 4, which is 0, 1, 0, 0, and minterm 8, which is 1, 0, 0, 0, I gotta change the value of this bit and the value of this bit. So it doesn't differ by only 1 literal. You know, if we write the expression, we've got, well, X, Y, W, X, Y, Z, but only this one is uncomplemented. And here we've got W, X, Y, Z, but only this one is uncomplemented. And you can see X is complemented but not, and then W is complemented but not. So these differ by more than 1 literal. So I can't put 4 and 8 next to each other. But I could put those 2 terms next to each other. They only change 1 bit. So that we got W, X. So this is minterm 12. I could put 12 next to 4. Okay. So now, next to 12 and 5, I need a minterm that only changes 1 literal. Let's see, well, 12 is here. 12 and 5, 0, 1, 0, 1. W, X complement, or no, this way. So they're both Y complement. They're both X. But if we move this way, let's see. W and Z are complemented as we go this way. So this one has got to be, well, we switch W maybe, and then we switch Z so that we can do that. So we got to change W or Z. Let's see if we can figure out which one it should be. These grids, now these two rows are all, they all start with a 0 and then 3 bits. So we only go up to 7. So we don't need that 4th bit yet. So these are all the things where W is 0. So if we can extend our kind of logic, I think this all is W. Okay, well that didn't help me too much. Oh, wait, maybe it did. If I've got 12 here, it's still got to be W. It's still got to be this one. But I have to move this way and get adjacent to 5. Now 5 has Z uncomplemented. 12 has Z complemented. So if we move this way and keep W, but uncomplement, so W, X, Y, Z. Right, keep W the same because we're in the W rows, but switch the complement status of Z so that here we've got Z adjacent to Z. Then 5 was this one, and this one and this one only differ by W. All right, cool. So this is 8 plus 4 plus 1 is 13. $12, 13. With similar logic, I'm not going to make us go through all of them. With similar logic, we can follow along. We can sort of guess that 12, 13, we want to put 14, but we can't because it changes too many bits. So we put 15, 14, and then 8, 9, 11, 10. We're still doing that gray code thing where we switch the middle two. Note that we still switched the middle two. We went 0, 4, 8, 12, but we switched those two. We 0, 4, 12, 8 instead of, oh, wait a minute. 0, 1, 3, 2. 0, 1, 2, 3, but we switched 3 and 2. 4, 5, 6, 7, but we switched those two. 0, 4, 8, 12, but we switched the latter two. And we've got this kind of gray code thing going on. That's the setup. If we want to finish labeling which rows and columns belong to which variables. All right. Now think about the min terms. 0, 0, 0, 1. That's, all right, 0, 0, 1, 1. I'm thinking about all of the ones that have the rightmost bit 1, which is essentially anything that's odd. And okay. Now, W, X, Y. Y is anything that has the second bit. So that's 3, 2, 7, yeah, 6. So I'm starting to think that this here is going to be Y. And if we write each of these binary numbers, the ones place is going to be, I'm sorry, the twos place, 1 bit away from the rightmost, is going to be 1. So that's the Y column. And I think that means that this all has to be X. each of these require that the 4's place is 1. And in W, X, Y, Z, X is the 4's place. All right, so we've got our K-map figured out, and we know, like if we simplify something, we know how to extract the variable expression because we know what lives in what rows and columns. So the next thing we need is an example. Let's see how this goes. All right. This is a long one. There's a lot of terms in this one. Down here. F is given by the sum of minterms. 0, 1, 2, 4, 5, 6, 8, 9, 12, 13, 14. Clearly not the best way to write this, including 11 minterms. There are bound to be some simplifications we can make here. But I don't want to have to write the algebra for all 11 minterms and then try to simplify it because I know I'm going to lose my place and I know I'm going to miss something and it's not going to be the simplest. So the K-map is really important here. All right, so let's see what we get. Middle. Okay. 0, 1, 2, 4, 5, 6. Because we skipped 7. 8, 9, 8, 9, right? Because those are in the bottom. 12, 13, 14, right? 12, 13, 15, 14. Okay. So here we have a block of 8 that are adjacent. And if we compare that to our deal here, we note that that's everything where the y bit is 0. That's all the minterms that use y complement. So that just simplifies to y complement. Now, what do we do? These 3. We could just combine these 2 and then combine these 2. And that would do the job. But I think we can do better because each of those terms, it's 2 adjacent cells. So it only reduces the minterm by 1 literal. So here we've got, this represents 2 terms, each with 3 literals. So we need, I think no matter what we do, we're going to need 2 gates. But are we going to need 3 input gates? Or can we reduce it to 2 input gates? Can we end up with Boolean expressions of only 2 literals each? We could do that. Or we could do that. Now, we already counted those, that's true, but that lets us combine these 2 that we still need to count in a group of 4. Now, a group of 4 reduces 2 literals, so now we've got a 2 literal term. And we can look and see that this is everything not W, not Z. So it's these 2 here. And we could do the same trick with that last one down there. Technically, it only needs a term by itself, but if we include it within its own square around the side of the board, we get a simpler expression. So this is everything x, it's in the middle two rows, everything x that isn't z. Now, you see the two z complements and you say, oh, we could factor those out. And you're right, but that wouldn't net us any simplification. We still need a 3-input OR gate and two 2-input AND gates. I guess we can maybe save and say that it's a, so if we write it with the z complement out, w plus x, if we only had 2-input gates available, this would be better because we don't need the 3-input OR. There's only one OR. Here's an OR with 2 inputs. That expression in parentheses is into an AND gate with Z complement, but that's only 2 inputs to that AND gate. And then that result gets ORed with Y complement. So again, still only 2 inputs. So this is maybe a slight savings, but now we need an OR gate, an AND gate, and an OR gate, instead of 1 OR gate and 2 AND gates. We still need 3 gates to do it. It's a little bit simpler because we can use 2 input gates, but it's about the same. Okay, let's try one more. This one, let's make it given to us not in sum of min terms. So F, A complement, B complement, C complement, or B complement and C and D complement, or A complement, B, C, D complement, or A complement, no, A, B complement, C complement. Okay, we know this is a function of 4 variables because we've got 4 letters floating around in our Boolean expression. We've got the A, B, C, D. All right, so we need our 4 variable K-map. We need the 16 grid. All right, so let's see what we got. Instead of A, B, C, D, all right, so we're used to talking about W, X, Y, Z, but let's put it in A, B, C order. So alphabetically, A, B, C, D. Okay, A complement, that's everything up here. B complement, that's everything up here. C complement, that's these two. A 3 literal expression in a function of 4 variables is reduced by 1 literal from a min term, which means it's 2 squares next to each other, because that's what 2 squares next to each other do in the K-map. They reduce by 1 literal. B complement, that's here and here. C, so that's these 4. D complement, so that's these 2. Here and here. A complement, oh, well wait, this is a min term. So this, wait, which min term is this? This is min term 6. because 0, 1, 1, 0. Minterm 6 goes here. 4, 5, 7, 6. Okay, so A, yes. Not B, so that's only this row. Not C, so that's these. All right, cool. Let's see what we got. The first thing I noticed was those. Wait, it works off the top and bottom too? Yep, it totally does. Make sure, put the two minterms next to each other. This is minterm 0. This is minterm 12. No, I'm sorry, it's minterm 8. This 12 lives here. This is 8, so that's 1, 0, 0, 0. We only changed 1. Here, we look next, we only change 1, but then when we look the other way, we change to the one that's next to this one. Yep, it works. It works. So that's everything not B. A square of 4 is a reduction by 2 literals, so I need one more. It's everything that isn't B and isn't C. All right. I see these two. And I can't think of another way to get this one involved. We could try to run up and up from the bottom, but we only have one here. That's a group of 3, and that doesn't do anything for us. So I think we do have to do these two. And that's everything. It's only 2 adjacent, so we only reduce by 1 literal. And I mean, it depends how you want to think about it. You can think about it as, you know, overlapping regions. So this is the region that isn't A, is C, but isn't D. Or, yeah. The other way to think about it, I guess, this rectangular region, the only variable that it's half in and half out is B. We've got one cell in the region of B and one cell outside. That's the variable that we're eliminating. We do still have to figure out whether it's A or not A. So, I mean, I guess we're, yeah, still kind of doing the same thing. Not A, yes, C, not D. And then there's this one. We could leave it alone. But we don't have to. See, here's the cool thing. We know that the map wraps from right around to left. 8, 9, 11, 10. 10 and 8 differ only by 1 bit. So it works this way. But we also know that it wraps top to bottom. This is minterm 8, 9, 11, 10. This is 2. Now 10 and 2 looks like 0, 0, 1, 0. 10 looks like 1, 0. Yeah, those differ by only 1 literal. So I kind of want to do this and bring this one in, because this one wraps around to this one and this one wraps up to this one. So we've got a corner on the outside. The outside 4 corners make a square. And that is a pretty neat trick. That's the simplest expression that we can have that includes this one square by itself, this one cell by itself. We've got a square that we can make with the four corners. So that's everything not D, everything outside of D, and everything outside of B. Everything not B and not D. And again, yeah, we could factor out the B complement and write C complement or D complement, and that maybe is savings, depending the chips we have available, if we don't have a 3-input OR and we, whatever. But that's 4 variable K-maps, and that's how they work. They take a little bit of practice, and it takes a little bit to remember the like weird kind of gray code sequence. I mean, we spend enough time trying to remember how the binary sequence goes, and now I'm trying to kind of change the order, but not really. So it does take some practice, but lucky for us, I've got practice on the horizon, right? It's coming. So that's this segment. On to the next one.